Now, the fact that a piecewise function is a function means that when we graph it, we will not have two lines in the same spot because that fails the vertical line test. A piecewise function, being a function, is just going to be a bunch of different graphs that may or may not connect at the barriers. If it doesn't connect at the barrier, then it's not continuous. If it does connect at the barrier, it's called continuous. But notice if there are two spots, one's going to be an open circle, one is going to be a filled in circle. Why? Because if they were both filled in, it wouldn't be a function. It would fail the vertical line test. So in order to be able to graph a piecewise function, you have to be able to graph lines. Before we even get into the piecewise function of it all, I want to say we know how to graph both of these things. We know how to graph y equals negative 3x minus 1. We know how to graph y equals negative x plus 1. So I'm going to graph them both. Y equals negative 3x minus 1. If we had this graph, would have a y-intercept of negative 1. So that would be a point. And then a slope of negative 3. Down 3, right 1. Or up 3, left 1. Either way, we would have this line here. Now, what this means, f of x equals negative 3x minus 1, if x is less than negative 1, that means that at this negative 1 barrier, where we're split less than and greater than or equal, when x is less than negative 1, we have this graph. So we have this graph everywhere to the left of this dotted line. Everywhere that the graph is less than negative 1. Where it's greater than or equal, we don't care about any of that. We only care where it's less than negative 1. And since it's not or equal to, that's a filled in circle. Now, how could we get this without graphing the entire line? Well, instead of the y-intercept, because that's not going to be useful for us, the y-axis isn't even part of the things to the left of the line. The line's at negative 1. If we plug negative 1 in, y equals negative 3 times negative 1 minus 1. Y equals positive 3 minus 1. Y equals 2. When x is negative 1, here at y equals 2, that's where our filled in circle would be. and then we build off of it. How would we continue to draw the line? Well, the slope is negative 3. Down and right, that's the wrong way. That's the wrong side of the dotted line. So we would go up and left. Negative 3 is negative 3 over 1. But it's also 3 over negative 1. So if down and right doesn't work out, we could go up and left. Up 3, left 1. Up 3, left 1. And there's our next point that we would drive through. So what about the right side? Well, the right side would be the graph of y equals negative x plus 1. We know how to graph this. It's a y-intercept of 1 and a slope of negative 1. Down 1, right 1, or up 1, right 1, or up 1, left 1, sorry. Negative 1 for a slope is negative 1 over 1, or 1 over negative 1. Down and right, or up and left. Notice up and left is going to fill that point in. So it's continuous. But the graph looks like that. So imagine we had the full graph. It would be like this. But since we're only interested to the right of the dotted line, everything to the left would get erased. So we wouldn't have however the line continues, because none of this matters to the piecewise function. We only want the part where x is greater than or equal to negative 1, where we are to the right or at negative 1. So hopefully, now that I've explained it this way, that this is two full graphs that we're cutting at negative 1 and we're putting together so that the right side of negative 1 is this one and the left side of negative 1 is this one. Hopefully, if you can grasp that, then the method I showed in the last lecture for graphing piecewise functions will make more sense. So how would I do this from scratch without thinking of it being two separate lines? Well, I make it all about the partition points. In this case, we only have one at negative 1. And I put a dotted line in there. And then I find all the filled in or open circles, endpoints on this line. Since this dotted line is negative 1, I put that value in for x in both of the functions. When x is less than negative 1, I use the top. So the top one is going to be an open circle because it's not or equal to. So top, that's going to be an open at negative 1. So for negative 3x minus 1, I put negative 1 in, and I get 2. So when y is 2, I have a filled in circle here X is -1, Y is 2. Now for the bottom. Since it's X greater than or equal to, this one is filled in. And I'm going to test X equals -1 in -X plus 1. That's the opposite of -1 plus 1, which is +1 plus 1, which is 2. So here I also have the Y value of 2. If it was anywhere else, it would just be a filled in circle, but since it's in the same spot, that means we have the same point here. So the filled in circle from the bottom is actually filling in the open circle from the top. Now that we have all of the filled in or open circles on the dotted line, we go left and we go right. We do the correct slopes off of the correct points. So for -3x minus 1, that's a slope of -3. -3 is either -3 over +1 or +3 over -1. So either down and right or up and left. Since we want to the left of this point, then down and right, that's not going to do. We need up and left. Up 3, left 1. We can go again. Up 3, left 1. We draw our line, but it stops at this dotted line. If it was the full y equals 3x minus 1, it would be the whole thing. Now here, -x plus 1 has a slope of -1, which is either -1 over +1 or 1 over -1. So it's either down and right, or it is up and left. Since we want to go to the right, we have the down and right one. Down 1, right 1. Down 1, right 1. Down 1, right 1. Down 1, right 1. So off to the right, we have this line with the slope of -1. So we have a slope of -3 until we hit this barrier, and then it changes to the one that has the slope of -1. But if it was the whole line, it would just keep going. We don't care about the stuff to the left. This is not a straight line. This isn't one of my drawings that went awry. This is actually supposed to look like, instead of a straight line, a bent line. Slope of -3, slope of -1. Hopefully that helps clarify piecewise functions. Average rate of change. Piecewise functions, a function that is defined by two or more equations over a specified domain. So these are these weird looking functions. And a function's just a rule. And this is a specific rule that has an either or. Either it's true that g is between 0 and 15, in which case the top rule applies, or it's true that g is greater than 15, and then the bottom rule applies. So to find c of 5, that means g is 5. G is between 0 and 15. That's the top rule. The top rule just says 40. So c of 5 is 40. Meanwhile, c of 50, that means g is 50. 50 is greater than 15. So we're in the bottom rule. We subtract 15 from 50 to get 35. We multiply 35 times 0.6 to get 21. We add 21 to 40. And we get 61. So C of 50 is 61. And that's how we use a piecewise function. We figure out if we're in the top rule, the bottom rule. Sometimes there's a third or more, just with different restrictions on the domain. Figure out which part of the rule we're in and then apply it. Graphing them is like graphing each individually, but then only picking the part that we want. Here, each section of the domain is going to be a different line. For instance, when x is less than or equal to -1, we'll have the line f of x equals 3. We'll have when x is less than 2, that line when x is greater than -1. So let's use a partial table of coordinates. And let's use x values -1, -2, and -3. That'll cover x less than or equal to -1. And when x is less than or equal to -1, the y value, the f of x, is 3. So no matter what we put in for x, as long as x is less than or equal to -1, we get a y value of 3. So -1, 3, -2, 3, -3, 3. Now, x less than 2, or sorry, x minus 2, if x is greater than -1. So these are values like -1/2, 0, and 1. Things that are greater than -1. And we subtract 2 from each x value to get our points. So we plot our points. We have an open circle down here at -1, -3, because that -1 is not included in the x minus 2 line, but everything to the right, including x equals -1/2 and x equals 1 and x equals 0, they are included. So we could imagine we have a dotted line where the domain separates at x equals -1. And to the left, we have one line. To the right, we have another. We can't have two filled in endpoints on the dotted line, though, because then it wouldn't be a function. So one of them has to be open. Hello, everyone. Today we're going to go over the Unit Exam 1 solutions. Let's get started with number 1. In number one, we want to determine whether the relation is a function. We're given the relation with 4 ordered pairs, -6, -6, -3, 7, -1, 4, and -1, 9. We notice that we have an x value of -1 twice with 2 different y values. When we have a repeating x value like this, by definition, it is not a function. So number one is not a function because of the repeating x value of -1. Number two, evaluate the function at the given value of the independent variable and simplify. We're given the function f of x equals 3x squared minus 4x plus 2. We want to find f of x minus 1. That means we plug x minus 1 in for every instance of x. So instead of 3x squared, we have 3 times x minus 1 squared. Instead of minus 4x, we have minus 4 times x minus 1. Then we have our plus 2. First, we want to expand x minus 1 squared. That's x minus 1 times x minus 1. That gives us x squared minus 2x plus 1. Next, we're going to do distribution. We're going to distribute the 3. We're going to distribute the -4. When we distribute the 3, we get 3x squared minus 6x plus 3. When we distribute the -4, we get -4x plus 4. It is a plus 4 because we have -4 times -1. That's positive 4. And again, we have our plus 2. Combining like terms, minus 6x minus 4x gives us minus 10x. And plus 3 plus 4 plus 2 gives us plus 9. So our final answer for f of x minus 1 is 3x squared minus 10x plus 9. If you got minus 10x plus 1, what most likely happened is that you did -4 times -1, but kept it as a -4. Number 3, evaluate the piecewise function at the given value of the independent variable. We have f of x equals 5x plus 4 if x is less than 4, and f of x equals -5x minus 3 if x is greater than or equal to 4. We want to evaluate f of 7. So 7 is greater than or equal to 4, which means we're going to be using the bottom equation. So plug 7 into the bottom equation, plugging into -5x minus 3. That's -5 times 7 minus 3, which is -35 minus 3, which is -38. So our answer for number 3 is -38 because we use the bottom equation because 7 is greater than or equal to 4. Number 4, we want to find the slope of the line that goes through the given points, and the given points are 7, -9, and 5, -2. 7, -9 would be our x1, y1. 5, -2 would be our x2, y2. And the slope formula is y2 minus y1 over x2 minus x1. So that's -2 minus -9, which is -2 plus 9, which is 7 on the top. On the bottom, we have 5 minus 7, which is -2. So we have 7 over -2. Positive over negative is negative overall. So -7/2 would be our slope. Number 5, graph the linear function by plotting the x and y intercepts. The function we're given is -3x minus 6y minus 18 equals 0. We want to put this into standard form by getting the x's and y's on one side and everything else on the other. So we're going to add 18 over to the other side, giving us negative 3x minus 6y equals positive 18. So we want to use intercepts. First, we have our x-intercept where y is 0. Plug 0 in for y. We get negative 3x minus 6 times 0 is 18. The minus 6 times 0 disappears, just leaving us with negative 3x equals 18. And dividing both sides by negative 3 gives us x equals negative 6. So our x-intercept is negative 6, 0. Our y-intercept is when x is 0. So plug 0 in for x. Negative 3 times 0 minus 6y equals 18. The negative 3 times 0 is 0, so that disappears, leaving us with negative 6y equals 18. Dividing both sides by negative 6 gives us y equals negative 3. So our y-intercept is 0, negative 3. Put that on the graph. Y-intercept of negative 3. Put our x-intercept on the graph. X-intercept of negative 6. And then draw the line through the 2 points. Number 6, find an equation for the line with the given properties. The solid line L contains the point 2, 4 and is perpendicular to the dotted line whose equation is y equals 2x. Give the equation of line L in slope-intercept form. So we have this dotted line. The dotted line is y equals 2x. We have this solid line going through the point 2, 4, perpendicular to the dotted line. Well, the dotted line, y equals 2x, has a slope of m equals 2. So the perpendicular slope would be the opposite reciprocal. The opposite reciprocal of 2 is negative 1/2. So we can start with point slope form. Y minus y1 equals m times x minus x1. Plug in negative 1/2 for m. Plug in the 0.24 for x1, y1. That gives us y minus 4 equals negative 1/2 times x minus 2. Distribute the negative 1/2. Negative 1/2 times x is negative 1/2 x. Negative 1/2 times negative 2. Negative times negative is positive. 1/2 times 2 is 1. So y minus 4 equals negative 1/2 x plus 1. The final step to get it into slope-intercept form is to add 4 over to the other side so that we have y equals. And 1 plus 4 is 5. So our final answer is y equals negative 1/2 x plus 5. You also could have set up y equals mx plus b directly for slope-intercept form. Plug in m, y, and x, solve for b, you would get a b equals 5. And you can get the answer that way as well.